So coming back to this simulation aspect, what we generally do after we get the simulation and get the optimized dimensions validated, that okay, we will be working with this type of with this particular dimensional structure only. So we get some results, and if these results are suiting our requirement, then we optimize them by something which is known as parametric analysis. What is this parametric analysis? Now suppose we get a particular bandwidth. I am talking in terms of this antenna only. Suppose we get a bandwidth from say 3 gigahertz to 6 gigahertz using a particular structure. That is acceptable, no problem. But certainly we would wish, is that the best which we are having, or the bandwidth can be enhanced? Suppose we are talking about a wideband antenna. So for that, what we need to do, we need to optimize the structure. We need to change the dimension of the structures a bit here and there and see whether we are getting a positive response or not. Positive response means whether we are able to enhance the structure or not. So that is basically parametric optimization. And once we see that we are having basically the optimized structure, the next step in any project is data extraction. Data extraction means exporting the data, exporting the information about the dimension so that we can actually prepare the hardware, which is known as a prototype. The dimension which we optimized, we need to export it to some vendor or to some third party, or if we have our own labs equipped with the fabrication devices, we can export it to our lab also from the system so that we can prepare the actual prototype from the exported data. The next step in any project is, from the extracted data, we will fabricate, we will actually manufacture the prototype. Finally, if we are manufacturing, if we consider that we have actually manufactured the antenna, we need to validate whether the results which the measured and whether the results which the fabricated antenna is giving us is actually matching with the simulated results. That means we will perform some measurements on the fabricated antenna, compare with the simulated results, and if they match closely, then we will say that our entire process flow is appreciable or acceptable. So that's our motive in this case. So let's see how we begin with the process. Now, as you can see in the screen in front of you, that the simulation platform which we will be using is CST Studio Suite. It is basically Computer Simulation Technology Microwave Studio Suite. The full name of the platform is this. There can be different versions. Now, I am using the 2019 version to showcase the different components it has, because this 2019 version is reported to be most versatile in terms of the easiness of the user interface, the accuracy of the results, and also the features, the optimization features that it can provide. Now, automatically a question may arise, why this particular software? Why this particular platform? Why not something else? To answer this, I should tell you that there are basically 3 electromagnetic simulation softwares present in the industrial level. One is this Computer Simulation Technology Studio Suite, which is developed by the Dassault Systems. Next is the ANSYS High Frequency Structure Simulator, popularly abbreviated as HFSS. And the third one is Altair Technologies developed FECO, FEKO software. So the two others, that means HFSS and FECO, they have some shortcomings in terms of the frequency range in which they can provide accurate results. For example, the high frequency structure simulator can give you very accurate results if you are simulating over high frequencies. FECO is comparatively a newer one, so it is yet to be tested for its credibility in electromagnetic simulation. This is where this computer simulation technology software stands out and makes itself the obvious choice in research domain also, in commercial, industrial level also. So we will have some knowledge gathering sessions and some hands-on training sessions in this CST Studio Suite. Now, what we will design and simulate today is basically a microstrip patch antenna using this Studio Suite, and we will examine the various properties, the various results of the microstrip patch antenna. So let's see how it is done. At the very beginning, we have to create a project template. See here, this option is there. We have to create a project template. These templates are already created by me for some research oriented applications, and these structures are already generated. So I won't show you them. I will design a structure from the scratch. Then I will perform the modeling. I will simulate. I will analyze and explain you the results. So first we need to create the project template. So we should click on this. Before I click, I will just tell you, see, these are the different modules which the CST actually gives you. This CST is only not suitable for antenna design. It has a foray of other applications also. 3D simulations, circuits, electronic circuits and systems also is there. Designing printed circuit board technology and different PCB packages can be done. Antenna Magus is basically completely oriented for antenna design. Filter design, chip interface, FEST 3D, Spark 3D, system simulator and IDEM. These different applications are there in CST. Many of these applications are completely industry oriented, I mean at a higher level. So we will not discuss this in this session. Maybe in some other future sessions we will be discussing about them comprehensively. Now another difference or another comparative analysis I think I should tell you in between CST, HFSS and FEKO. See, I told you that simulation is basically a mathematical modeling. So these different simulation platforms, the CST, the HFSS and the FEKO, they basically use different types of mathematical models. Accordingly, 3 mathematical models are there which are mostly used by industry persons or research oriented applications. They are the finite integration technique, FIT. Next is the finite element method, FEM. The third one is finite difference time domain, the FDTD method. So each of the simulation platforms, they use either of them. Our particular simulation platform, CST Microwave Studio, uses finite integration technique, FIT algorithm. It's basically a complex algorithm. I mean, where you can feed the data set and you can get a particular output in the form of a pictorial representation. Along with this, we have some curve fitting applications that also I will detail. So let's start off. First of all, what we will do, we will create this project template. So we are clicking over this. Again, different options are coming. Microwave and RF optical, EDA and electronics, electromagnetic interference, electromagnetic compatibility, which is popularly abbreviated as EMI, EMC. Next we have particle dynamics. Then we have statics or low frequency applications. Now one thing I should tell you here, that although the ANSYS HFSS software is predominantly used for high frequency applications, in terms of frequency coverage, CST is very versatile. That means that CST is equally well adaptive for low frequency applications as well as high frequency applications. And this can be treated as another reason why CST is used much more profoundly than the other simulation platforms. So what we will do, I mean, among these 5 options to design an antenna, to design a planar antenna, patch antenna, we will select this microwave RF optical, this option. The moment you click it, you will have these options coming in. Antennas, circuits and components, radar cross section, biomedical exposure, okay, SAR values, optical applications, periodic structures. These are high level structures. Okay, these are also antennas, but these are high level. So we will start from a basic level now. So we are designing antennas, so we will select this. Next we will go to next. Now in between antennas, again there are 8 options, 8 different types, 8 broad types of antennas you can actually design and simulate using this CST suite. First is this waveguide. I mean, you can actually simulate those horn antennas, conical antennas, dipole antennas, Yagi antennas using this CST only. Okay, actual big 3D structures. So they are known as waveguide antennas. This is the mostly used planar antennas, patch antennas, slot antennas, okay, like this. Wire antennas, all of us know what a wire antenna is basically. Okay, it can be casted as a monopole or a dipole. Phased arrays or unit cells, mobile phone or integrated smart antennas basically, reflector antennas, dielectric resonator antennas, and RFID, radio frequency identification antennas. We will start with the most basic form, which is the planar antenna. Now what I told you previously, that this printed antennas, they are basically casted on a single substrate, single block, that basically renders a planar structure to the antennas. Okay, although they have some height, length, breadth and height, although they have this 3D sense, but they are considered to be planar because the entire antenna radiator structure is limited to, can be limited to one plane. I will show you in this simulation only, I will show you what that means. So we will select this planar, patch, slot, etc. This second option we will select. So after that we will put next. Automatically 3 options come: time domain, frequency domain and multi-layer. Now see, there are some options mentioned here, that time domain for wideband or multiband antennas, frequency domain for resonant antennas, and multi-layer antennas for some infinite dielectrics or ground planes. Okay, but this does not mean that you cannot use time domain for resonant antennas. You can't use frequency domain for wideband antennas. It does not mean so. But if you use time domain for wideband antennas, as it is mentioned here, you are expected to get the optimum result. For example, if you use frequency domain for resonant antennas, you are expecting to get the optimum results that the system is informing you. Now the choice is yours. So basically we will go for the with the system what it is defining, we will go with that only. See here, selecting this time domain or frequency domain or multi-layer is basically setting up the solvers. I mean, you will be giving a data set, the system, the platform will solve that data set and it will give you the result. So basically what type of solver we will use, this definition is related to that. So see, this solver is highlighted. So we are basically selecting what type of solver we will work with, time domain or frequency domain or multi-layer. We will fix up or we will abide by the default setting here, which is the time domain, because we are designing a wideband antenna. Okay, wideband or multiband antenna. So time domain is automatically selected. We will put next. Next is the units. See, we will define the dimension. We will define the frequency. We will define, since time domain is there, we will define the time scale, and also temperature is also required to be defined. Although manually we won't do so because the platform is actually selecting the temperature scale and the time scale. So we won't tamper anything with these 2 options. We can certainly change this. That means suppose you are designing an antenna, you will be giving the dimension, you will be feeding the dimension into the system in centimeters or in millimeters or in decimeters, whatever. You can make a choice. See, if you drop down, you can make a choice. Conventionally, it is advisable to keep the dimension in millimeter only. Why I will say so? Generally, planar antennas work on the gigahertz, lower gigahertz range. For lower gigahertz range, the dimension of the antennas is basically in the order of 10 to the power minus 3 meters, which is 1 millimeter. So we will consider the dimensions in millimeter only.